In this fifth and last item on our first test in 2016, we've got two shafts of two different materials bonded together with a torque. The shafts are of the same length, under 57 inches, and we have applied torque of 15 kip-foot, and we're asked to find the shear stress in each material at the interface location, which happens to be, we've got a 6-inch outer diameter, 1/4 inch wall thickness, so that means that that's right at that interface, that little distance right there. Let me zoom in a little bit here. We'll probably have to go to multiple pages here. First step is to take a look at equilibrium. So let's get our free-body diagram in. Here's point B to the right, and so we've got our applied torque of 15 kip-feet, and then we've got a resisting torque. Notice the outward positive normals for the unknowns, and our resisting torque here, the T2 and T1. T2 represents steel, T1 represents the aluminum, and we have a nice straightforward relationship here that obviously 15 is going to have to equal T1 plus T2. That's two unknowns in one equation, so that's statically indeterminate to the first degree. Right, so we're going to have to think about our displacement relationships. And the easy, obvious thing here is that the rotation that happens at B relative to A is going to be equal to the angle of twist for the outer aluminum and the inner steel. Those two are going to be identical to each other. And so that's nice, because now we go straight to our force displacement relationship, force in quotes, because of course we don't have a force here, we have a torque. So you could call it the torque displacement relationship. The equation, of course, generically is phi equals TL over JG, or you say T over K sub T. That's just the generic equation. For our situation then, we've got that the T1 L1 over J1 G1 is going to be equal to T2 L2 over J2 G2, right? And of course, I'm already using the compatibility equation that we have up here. The lengths are the same, so we can get rid of those, and we're going to find out that T1 must be equal to the ratio of J1 to G1, or J1 G1 to J2 G2, and then we got the times T2. So let's go figure out what that relationship is. Remember, T1 is the aluminum, so it means T1 equals J1. We're given the polar moment of inertia already for that one. It's 11.90 pi inches to the fourth over the J from the other one, 15.78 pi, and then times the ratio of the shear moduli, 3,600 KSI over 11,200 KSI, of course, times T2. And what do we get then? The pi's obviously cancel out. 11.9 divided by 15.78 equals times 3,600 divided by 11,200. And we get 0.242, and 4 times T2 is our T1. Right, so that means that we can now go back and solve for our individual torques. Substituting into our equilibrium equation, we've got 15 equals T1 plus T2, and that's equal to 0.2424 T2 substituted in plus T2, and so 1.2424 T2. Therefore, T2 is going to be equal 12.07 kip feet times 12 to get it into kip inches, which will be handy in a moment. So that will be 144.88 kip inches. That is so far exact. And then we can add that to the take the opposite of it, add it to 15 kip feet, which is 180 kip inches. And so our T1 is equal to 15 times 12 minus 144.88, and that's going to be 35.12 kip inches. Right, so that's our individual torques, and now we just got to remember how to go find our shear stress from the torque in each material. It's like we might squeeze this into one page. And of course that expression is that tau equals T rho over J. Now we don't want tau max in the material, we just want it at any old radius. And so for the first material, that'll be T1 times our rho of 2.75 inches over J1. So that's 35.12 times 2.75. Right, that's kip inches times inches over J1, that's 11.90 pi inches to the fourth. So we'll get kip inch squared over inch to the fourth, that's KSI, that's good, we got the right units. 35.12 times 2.75 divided by 11.9 divided by pi, and we get 2.58 KSI. And likewise for the last one, Tau 2, that's the inner one, that's the steel one, that's T2.75 over our J2, that's 144.88 times 2.75 over 15.78 pi, and let's see what we get. And that will be 8.04 KSI. And note that the shear stress in the steel is different than and much larger than the shear stress in the aluminum, the outer, and that's because the steel was so much stiffer. It was so much stiffer for two reasons. One, it has a much larger shear modulus, by almost, not quite a factor, really more like a factor of 3, right? Not even close to 4. It's about a factor of 3. And so it's much different material. And even though it has a smaller radius, and when you go to calculate J, if you wanted to, of course that J, if you wanted to just spend some extra time on the test, pi over 2 times the outer radius of that material minus the inner radius of that material, those are raised to the 4th power. And so you would think the aluminum would be much bigger, but the thing is that you've got a lot more material for the steel than you do for the aluminum, right? Wall thickness is double in the steel, so that compensates along with the 3 times larger stiffness and shear of the material. And so that's why you see that T1, the outer torque, is much smaller, quarter of the inner one, is because of that relative stiffness. And that contributes significantly to why you have this much larger shear stress in the inner material than you do the outer material.